Okay, so energy-wise, a good way to kind of split energy is energy that is being energy that's being in action. Okay, kinetic energy, or energy that it's called potential energy. It has the ability to have it for energy to be on or spent. Okay, potential energy, kinetic energy, and potential energy. Now, these are some different forms of energy. It's kind of neat how a lot of times these forms of energy can be kind of morphed from one form of energy into another form of energy. But these are just kind of some different forms of energy. Kind of focusing on kinetic energy. So kinetic energy, abbreviated KE for kinetic energy, is the energy associated with motion. And one of the cool things about motion or kinetic energy can be motion on the large scale. So for instance, if you have a cart and you give the cart a push, you actually are taking energy and making that cart move. As that cart moves, it has a certain amount of kinetic energy. It's like kinetic energy is 1/2 mv squared. So the mass of the cart times the velocity it's going squared, half that. So that's kinetic energy. But matter, just regular old matter, like this table has a certain amount of kinetic energy. Okay? All matter is made up of atoms, and all atoms are moving, and that's kind of what's being shown here. So if kinetic energy is associated with motion, then all matter has kinetic energy. Okay. Now, the cool thing is if you take matter that has a certain amount of kinetic energy, and if you cool it down, what happens to the motion of that matter? Cool it down. It slows, exactly. It slows down, and actually you could calculate its kinetic energy is less as it cools down. It cools down, it slows down, it has less kinetic energy. So we'll be talking a lot about water molecules in here. Okay, so those of us who have, drink water or whatever, the little liquid water molecules in here, they have a certain amount of kinetic energy. So I brought a thermometer here today. Okay. So one of the things I want to emphasize is when you stick a thermometer in a liquid, okay, or a solid or a gas, okay, you are measuring the kinetic energy. The temperature is an indication of the kinetic energy. It's just an indication, though. I like to kind of think of it as kind of pings and makes the liquid go faster in here, and it expands, and then it creeps up, okay? If your liquid cools down, okay, it goes slower, less pinging, and as this liquid cools down, then it contracts, and the liquid will come down, okay? So temperature is an indication.
If something's frozen, does it still have kinetic energy?
Yes, if something's frozen, it definitely still has kinetic energy. There is this temperature called absolute zero, I think we'll probably get to, that actually at absolute zero, water would be, let's see, that's negative 273 Celsius. So water freezes at 0 Celsius, and you could take solid ice and cool it and cool it and cool it to negative 273 Celsius, and at that point, the water molecules would not have any motion. Yeah.
Would it even look like solid ice? Or?
Well, see, that's just it in science. There are these things that you can approach, but you never really quite attain, because you cannot cool something down to 0 degrees Celsius.
So it's a theoretical.
It's a theoretical, but it still would look like water molecules at negative 272.
So I haven't done that.
Right, they haven't done it yet. I know. There's always talk about it, but no, they have not done it. Because it's like a basic tenet of matter. All matter has motion, and if it's at less than absolute zero, it has no motion, so it's not really matter. So, you know what I'm saying?
So it defies what?
Yeah, it defies, exactly. So one of the things we're going to talk about in here is phase changes, okay? So throwing plasma out the door, the three main physical phases of matter are solid, liquid, and gas. Okay, so I'm going to draw little boxes down here. This is going to be actually I'll put an S for solid. This is going to be, I'll put an L for liquid, and this other little box is going to be a G for gas. And with regard to motion, and we can pick on water if you want to. Okay, water gas would be what? Water vapor. So I'll kind of start over there. If this is H2O vapor, okay, if I'm going to look at those water molecules, they are going to be running around. So each one of these dots is an H2O molecule. okay? You can't tell they're running around, but can you see the wide spaces between those water vapors, particles? And then in physics, they do a great job of using these things called vectors, where basically it's just a line that says what direction the water molecule's going. The longer the line, that means the faster it's going. So here I am showing you these water molecules. The length of the line is showing you those water vapor particles are just crazy. The cool thing about gases, including water vapor, is they will fill your container, okay? They will bounce against the sides of your container, creating something called pressure. Okay, it's wonderful. And so let's just kind of back down here to, this would be ice right over here. This would be H2O ice, okay? So if we contrast those two, now for ice, I'm gonna, and I've had a student tell me before, it's like they're cold, they like to bundle together, like they're close together. So down here are my water particles. And it might be hard to see, but each of those is like a little dot. Those are my water particles. And I have a figure kind of showing you coming up. So they're close together, okay? And then if I were to show kind of the little bit of them moving, it would just go like this. And I'm not going to do it for all of them. But it would just be kind of, okay, they're just barely moving. Okay, so over here, what I'm trying to show is this is over here, and it's as an ice cube. We have low KE for kinetic energy. Okay, but there it's got some kinetic energy. Okay, and over here we have high kinetic energy, high KE. So that's kind of matter in its solid, liquid, and gas. Now, liquid is just kind of both, kind of between a solid and a gas. So that actually leads us into a slide from here. But this slide is to kind of try to convince you that when you use a thermometer, we're getting, what you guys know is the temperature. We're getting the temperature of the air, the temperature of the liquid, okay? The temperature. Now, temperature is an indication of how fast those molecules are going, and how fast they're going is actually kind of balled up in what we call their kinetic energy. But this temperature in and of itself does not say how much thermal energy or heat an object has. A good example of that is if you were to here's a cup of water, here's my cup, and here is a bathtub of water. Maybe not look like it. But let's just say that they're both at a toasty, it's easy to go on the Celsius scale because what temperature does water boil at in the Celsius scale? 100. So let's go on the Celsius scale. Let's go 98 degrees Celsius, 98 degrees Celsius. So I could stick my thermometer in both of these and it would read 98 degrees Celsius, right? But they're at the same temperature, but which one has more thermal energy?
Maybe the bathtub.
The bathtub. Why does the bathtub have more thermal energy?
Large surface area.
More water. More surface area, more water. So this has more, I'll say, thermal E, okay? Thermal energy. Now, thermal energy is one type of energy. Actually, thermal energy and heat energy are the same thing. More thermal energy, more heat. Exactly. So, you know, thermometers are great. They can actually tell us give an indication of how fast the molecules are moving. But if you want to point to a substance and say it has that much thermal energy, then you guys told me that you need to kind of say what is the mass of that object too, how much thermal energy it has. You can say what temperature it is, okay? But that's only one piece to say how much thermal energy it has. The third piece to say how much thermal energy is kind of what we say, kind of what the object is. Is it water? Is it air? So it's not just mass, it's not just temperature, it's also kind of what we say the nature of the object. All right. So, on the board here, I think, I'm going to go ahead and make a solid, liquid, and gas. Actually, you can see this on the next slide, on the next figure. So this is matter in its solid state, just water. We're talking about water. So this is ice, right? This is liquid water, We just usually call this, it's funny, because when water is a liquid, we call it water, right? Okay, and then over here, here's water in its gaseous state, and we call this water vapor. Okay, and so I drew these kind of close together with just small arrows. I drew these far apart because they'll fill the container with big arrows, lots of kinetic energy. And here I would draw them kind of moderately close together, moderately what we say connected, okay? And I would draw them kind of an arrow in between. That's kind of how much motion they have. That's what I mean liquid. So if we were going to take an ice cube and melt it, what would we do?
Apply heat to it.
Apply heat to it, exactly. So, apply heat. And remember, heat is thermal energy. I like it. So, if we were gonna go from liquid water to gas, apply more heat, right? Good. Can't spell. Okay. So, actually, this heat that you apply to change its phase is called latent heat. That's it. It's called latent heat. Okay, latent heat. And where does the heat come from, like when you melt an ice cube? It depends on. What if, let's put it this way, what if we were just to take a beaker of ice and put it here and come back later and it would be melted? Where did it get that heat from? The room, exactly. So you're applying heat, so we're taking it from the room. So actually, we're robbing heat. Heat is being transferred from the room into our water. Okay, so it's coming from the room, from the environment or whatever. Okay, so that's latent heat. Now, what we just described, we call this melting, right? The term up there, melting. Okay, we call this evaporation, right? So the opposite, though, if we were to go the opposite way, I'll switch colors now to red. It's not so intuitive, but, and it has to do with latent heat, we call it latent heat. Actually, as water goes from water vapor to liquid water, okay, we call that condensation. Okay, these are words you're probably familiar with. And in this case, we don't apply heat, but heat, I say, is given off. Given off. Heat is given off. Latent heat is given off when water goes from a vapor to when it condenses. Now, kind of like you said, in the case of melting ice cube, it got it from the environment. Honestly, as heat is given off, it's given off into the environment. One of the cool things about you guys who are into clouds or whatever, okay, clouds are this. Clouds are water that is in its liquid state. That's why they look milky white, because they're liquid particles, okay? When clouds are formed, they basically take water vapor and it condenses to form liquid water. Heat is given off, and so actually it makes, your clouds are by nature kind of warm. And what do we know about warm air?
It rises.
It rises.
So that's what causes thunderstorms.
That's one of the lifting things, yeah. Okay, exactly. So just by condensation, it wants to rise. Okay, so let's do this one. So what do we call the phenomenon when water goes from liquid to ice? We call it freezing, exactly. And heat is given off. I know it sounds weird, but like I've read, and I think this might be in this version of your textbook too, like if fruit growers in Florida are worried about frost, they actually can go mist their plants, because when that liquid water freezes, a little bit of heat is given off to the plant. You're like, really, dude? You really want to do that to your plants? Okay? But that little bit of energy given off during freezing can help save your plant. Cool. I know. So all of these little bits of heat, and I don't have a number to go with them, but there's a number, trust me, it's out there. How much energy do you need to zap your ice cube with in order to get it to melt? There's a latent heat of what we call fusion. You know, how much heat do you need to give it to go from a liquid to a gas? Latent heat of evaporation. Okay, there's a number there. Okay, but so that's it. Latent heat. And do you see where something is, if this is what's happening in the environment, whether it's, and one more thing, and it's actually, do you see where, let's see, in both of these cases, going from left to right, we said heat is applied. And both of these things, going from right back to left again, heat is given off. I guess that was the only thing I was going to say. Oh, yeah, my slide says, instead of, I think it says I use the word required, absorbed or released, okay. So heat applied, I'm using the word absorbed, okay, from the environment to the system, water. And here, in this case, it's released. Heat given off is, in other words, released. Goodness. Something like that, released. All right, cool. So this is a figure from your textbook that basically does what I just did. These are all latent heats from left to right. Latent heat is absorbed from the environment to your water that's doing its thing. From right back to left again, heat is given off. Okay. Now there are a few other terms on here I want to point out. It is possible, and I'm going to tell you the example, you've seen it before. It's possible, this word up here, sublimation. Notice how your author has drawn straight from a solid to a gas. It's called sublimation. Let's see, water. But if you've ever played, you should never play with it because it's very cold, but the stuff you can get from Hy-Vee, the dry ice, okay? Dry ice is basically not water, but dry ice is carbon dioxide that's solidified. And the way they got carbon dioxide to make a solid chunk like that, which really totally freezes your fingers, dry ice is on great pressures and low temperatures. They give it to you, okay? And one of the things about dry ice is, you probably noticed, it basically goes from a solid to a gas. Okay, it skips the liquid stage, so it sublimes. Probably an example of sublimation that we don't, we're buying a new house, and our new house does not have an ice maker. Oh my goodness, I think we'll survive. But anyway, if you don't have an ice maker and you make your own ice, actually there's a good chance that if you put your liquid water in your freezer dutifully, and if you come back 2 weeks later to get your ice cubes, good chance your ice cubes, they won't be there. They're gone. What's happened actually is sublimation. Yeah, do you ever make your own ice cubes?
Yeah, every day.
Do you? Well, if you leave them in there too long, have you ever come back and they're not full, they're kind of dinky? They're dinky.
Okay.
They might not be gone, but they're,
That's crazy.
yeah. And so what happened is, like, a few hours after it was there, it solidified. And then the longer you left there, basically it sublimed. It went from a solid to a gas. And I think freezer burn is where it basically backs on your stuff.
And that's why you have to remove the ice cubes after so long.
Yeah, don't
Even
leave
from
them in
an
there.
ice maker.
Oh, yeah. They get not tasting as good.
That's what that. I was wondering.
So the other one up here actually is along the bottom, and I'll tell you a good example of this one, deposition. It's possible what water does is it goes straight from being a water vapor, okay, to being solid.
The opposite.
Yeah, it's called deposition. It skips the liquid state. A good example of this is frost, okay? Say it's 20 degrees, this would be Fahrenheit, 20 degrees Fahrenheit, and you know 32 degrees is the tipping point for water to freeze. And over the course of the night, basically water vapor, okay, basically slows down enough to go ahead and what we say deposit on your blades of grass or whatever, your windshield. It skips the liquid stage. It goes straight from being water vapor to being a solid. That's frost, okay? You're still thinking about those ice cubes, aren't you? Well, I don't feel so bad. So you make your own ice. It's not too bad. We can do this, okay? Okay, it all works. Yeah. All right. Good. So that's latent heat. So latent heat basically is a transfer from the environment to your liquid water, or from your liquid water to the environment. Now there are three other important ways of getting heat thermal energy from point A to point B, and they're kind of summarized on this slide. How do you get heat from point A to point B?
You boil
Yeah, what's that?
it. You boil
You
it.
boil it. That's one of them. All in this actually are the 3 different ways of getting heat from point A to point B. One is convection. Convection is basically a blob. A minute ago, you guys told me if you take air and you warm it, that chunk of air is going to rise. That is convection. That warm chunk of air relocates from point A to point B. That's convection. So being shown here is liquid water. Like if that's a pan there, which I wouldn't like to be the guy holding that pan over the campfire. But so inside basically the bottom of the pan gets hot. That's why kind of the pink color. This is hot. I like the figures in this textbook. Okay, the top part of the pan is cooler. So basically, and water is mobile. So basically, it heats up, and as it heats up, it expands. Okay, and it basically becomes what we say buoyant or less dense, and it rises. As it rises, it cools, and when it cools, it wants to fall back down again. So we have these kind of what we call convection cells going on. It's like a lava lamp, if you've done the whole lava lamp thing. How do lava lamps work? They have like a little heating element down here, or a light, basically, which is both functional to heat and pretty. It lights up your lava lamp. So it heats the blob closest there, and as the blob becomes heated, it expands, and now actually since it's expanded, it's a little bit lighter, a little bit less dense, and it wants to rise. So it rises and it cools and falls back down. Lava lamp. Convection.
Aren't they like a fire hazard being in?
Lava lamps are a fire hazard? It could be. Could be.
Heard that.
Yeah. I'm hoping, there was lava lamps back in the 70s, and I hope the newer ones are better, but no. I don't know if it's worth the risk. Watch your lava lamps. So the next one of getting heat from point A to point B is conduction. Okay? So conduction's being shown here. Remember I said I wouldn't want to be this guy holding the pan, okay? So conduction is like, it's like a chain of molecules that are in contact with each other, and basically they bump each other, and it bumps kind of on down. So conduction is from molecule to molecule to molecule. Okay. And like this, if you're ever asked in a question or whatever, when in meteorology, rising chunks of air, convection, very important. The last one, radiation, very important in meteorology. This one, conduction, the not so important in meteorology. So the last one we're going to spend a little bit of time talking on in a few slides. It's generally called radiation. And it's funny, as I say that, you're like, radiation poisoning, radiate our food, okay? I mean, which can be a good thing. Actually, irradiating our food actually is a way to cut little microorganisms. But radiation in general just means a type of energy, okay? I think if you go back a few slides when I talked about mechanical energy, chemical energy, electromagnetic radiation, the last one listed there, that's this radiation. Now, the thing about radiation that's unique to the other two is it happens in a vacuum. Basically, radiation is so cool. I'm going to kind of show it as kind of a wave going through space. This is radiation, okay? And it can happen in a vacuum. It means it does not need any particles to go from point A to point B. Radiation just goes. Actually, a type of radiation is infrared radiation, and we kind of use that synonymously with thermal energy. So radiation coming up. But the radiation here is just kind of showing the oozing, and I would even put IR radiation here if you want to. We're going to see there's different cousins of radiation. There's IR, which is infrared. We talked about UV, which is, what's UV radiation? Ultraviolet, exactly. Visible light is a type of radiation. X-ray is a type of radiation. Radio waves is a type of radiation. So in this case, it's just, I would call this IR radiation kind of coming up from, okay, it doesn't need it doesn't need those little air particles, it's just going. Actually, it's going at the speed of light. Okay, so just to kind of show you the idea of convection, okay, one of the things we're going to talk about later is if you wear a dark shirt on a sunny day, you get hot. And that's actually kind of what's being shown here. The sun can shine, for instance, on green areas and brown areas, okay? But it's conceivable that that darker colored plot there is like sucking up more thermal energy than around it, okay? So if that's the case, it can create this little bubble of air, okay? And then like I mentioned, for those of us who love clouds, okay, that kind of convection of that warm chunk of air wanting to rise, actually it rises and it gets bigger. Remember I said how the weather balloons can actually get as big as the size of a house? Okay, so it gets larger and it actually cools down, and it can cool down to the point of basically liquid happening within that chunk of air. And that's basically at the crux of cloud formation. So convection's important. All right. Conduction, not so important. Now we're on to radiation.
Can you make the assumption that, it was kind of hard to say, but can you make at least the observation or assumption, that is, that there's more precipitation over the city, maybe?
He said, can you assume or would think that there'd be more precipitation over a city
Than the countryside.
because the cities are warmer and they have more convection? That's a player. That's a player. Yep. There's this thing called the urban island heat effect, and basically cities are little toasters, and so. But then you also have to have moisture and but yeah, good idea. So the different cousins of radiation. I list a few of them up here, but actually I brought this poster, which is probably more work than it's worth. But when I talk about cousins of radiation, they're like X-rays. These aren't all of them. Visible light, radio waves. Okay, they're different cousins of radiation. So I just thought this poster, I bought it years ago. I just thought this is so cool. And it's actually got different cousins of radiation than we necessarily kind of go into. But you see the gamma rays, X-rays, ultraviolet, and there's some overlap here, right? There's kind of some overlap. Visible light, and of all these cousins, that's how much visible light takes. Okay, and actually you can morph these, probably the higher energies into the lower energy. Like for instance, as I've been saying them, cosmic rays, gamma rays, X-rays, they all sound dangerous, and they are. Okay, visible light, not so bad. Infrared, I already kind of told you, be thinking kind of heat with that. Microwaves, radio waves, and radio waves actually have a low frequency. We have high frequency and low frequency radio waves. So those are the energies, and this is kind of where you use them, how you use them. We're going to talk more about this column over here. This is wavelength. And so a minute ago when I kind of did this, like for radiation, okay, as I kind of went up and down and up and down. Actually, if I go up and then I go up again, if I get the distance there, that's what this wavelength is. So up there is the shortest wavelength, and down here is the longest wavelength. The more dangerous ones, short wavelength. Okay, down here, long wavelength. This is crazy. Did you guys know, you probably did, that actually radio waves, I mean, we're talking, a repeating unit of a radio wave is like, more than 2 miles. 2 miles. A repeating unit of an X-ray is, like, would it be smaller than an atom? I'm thinking maybe. Okay.
So the old wives' tale, you're not supposed to stand in front of a microwave. Why is that?
I don't know. I'd have to look into that. Lily's saying, so like microwaves, you're not supposed to stand in front of a microwave?
I was told it's dangerous because of the radiation.
Yeah. I think that raises a good point. I don't think these are necessarily, these could be too much heat would kill you.
Right.
Okay, too much microwaves would kill you. So I don't know about radio waves. And some of these actually we use in medicine. We use them for imaging. We also use them for treating, kind of carefully treating cells. So, but as far as the microwave goes, I would follow your instincts. Don't hug your microwave.
Well, yeah.
Again, I hope they're like kind of lava lamps that they've improved over time. But
I was just curious because I thought of that.
Dark.
Yeah.
I do it anyway because
You hug your
I
microwave?
don't hug it. I stand in front of it
Yeah, I do too.
because I don't like waiting, so I stare at the food.
So,
You definitely can feel the heat off the microwave.
Yeah.
yeah, as long as it's thermal energy. Microwaves are so cool. Do you ever think about this? You're like, if about the time I think I'm smart or whatever, I'm like, could I ever make a microwave? No. Could I ever make anything? No. You know, how help. So this actually, again, the different energies. Now, the wavelength, actually, we use the Greek letter lambda. So if you ever see this for this thing that kind of looks like a upside down V with a tail, okay, that's wavelength. And that would be like this says over here, I think this says centimeters. Wavelength in centimeters, which is kind of strange, but that's okay.
Isn't it usually nanometers?
Yeah, it depends on which frequency it is. Like wavelengths for radio waves would be kilometers, and you know, wavelengths for those up there would be like picometers or nanometers or angstroms. But what I want you to kind of, it's on the next slide, what I kind of want you to know is the order of the cousins, the order of the, you know, the families. Like, you know, we have gamma rays and then X-rays and then ultraviolet, visible, infrared, microwaves, and radio waves.
What's an angstrom again?
What's that?
I never learned an angstrom.
What's that?
What's an angstrom?
An angstrom? It's like it's off by a factor of 10 from a nanometer. Yeah, but it's a metric thing. So it's got like an A with a little circle over it. So here are the cousins, and what I like to tell students is you might want to put this on your note card that you're going to bring with you to your exam, just in general, kind of know the order.
Just the gray ones this way, from that way, that way.
Probably from left to right, kind of the strong or the most energetic, the shortest wavelength. So up here, I say, so if you were going to answer this, which energy is most energetic? You would say, I would say gamma, me too. Gamma rays, get your ray gun going. Okay, so which energy then has the longest wavelength? You would say
The long way.
the longest
That's
wavelength.
pretty easy.
Yeah.
Oh, radio waves?
Radio waves? I would say that too. Okay, so that's kind of what I'm after. Now we can also, some of you may know who've kind of dabbled in electromagnetic radiation. By the way, this is called electromagnetic radiation. The whole thing is electromagnetic radiation. You know that actually you can also link up frequency. So the short wavelengths has the highest frequency and the long wavelengths have the lowest frequency. But I'm just worried about wavelength right now. Cool. There we go. Oh yeah, one other thing. Down here in the corner, this was actually a student one year told me, have you ever heard about a way to remember the colors? Now, remember visible light, so when it says light, that's visible light. It's like totally just a little small compared to all the other forms of electromagnetic radiation. But there are times, and they're coming up really soon, when it's helpful to know the order of the colors. Okay, so if you've ever seen a rainbow, this is the order that the colors should be in. And they're going from longest to shortest wavelength. So, like I had red, orange, yellow, and then green. It's like a name, Roy G. Biv. And then I have green, blue, and the color indigo, which I have heard on a podcast not that long ago, that the reason there are 7 colors, oh, and the last one over here is V for violet, so that's kind of from longest, long to short. The reason there are 7 colors instead of 6 is because I think it was Newton, Isaac Newton. He wanted 7. He didn't want 6. So 7's a prettier number or something. Yeah, anyway. So because for me, I stands for indigo, and you're like, dude, I've never even played with that crayon in my box. Indigo. I stands for indigo. And the other ones, you know, red stands for, R stands for red, orange,
So should I say
yellow, green,
Roy
blue.
G then?
Roy G. Biv, yep. Oh, yeah. Roy B. Biv. Oh, my gosh. Thank you. Yeah, this should say G. Thanks. Roy B. Biv.
Could you repeat that?
Sure.
Roy.
Roy, and this should be a G, like as a middle initial, G. I always think of Biv, and I think of Biff, like Back to the Future, and, yeah. So, Roy G. Biv. So those are the cousins. Okay? All right. So when I say laws of radiation, I mean laws of what these guys do. Okay? They follow some rules. It's awesome. In science, we have hypothesis, and in science, we have, remember from a hypothesis, you can make it a theory, yep. And then we have these fundamental laws, which are kind of cool. So laws are something that you can use in your hypothesis, but a law is just the way it is. Okay.
Gravity.
Yeah, law of gravity is a law, exactly. There are different gas laws. It's just how gases behave. Okay, these are the laws of radiation, so this is how these guys behave. Okay, one of the things is that all objects, if you were to have the right sensing device, okay, all objects ooze all these forms, well, all objects ooze forms of radiation. It's called black body radiation. How they ooze it, what they ooze, actually is related to their temperature. Okay, so I'm going to kind of show you these things called radiation curves that kind of show you what kind of energies the sun emits at these different wavelengths. So in general, if you're to look at these curves of what an object is emitting, the hotter the object, two things, the hotter the object. One is basically when you look at that curve here in a minute, along the y-axis is intensity. So basically they emit more radiation along the y-axis. Their peaks are higher. Their curves are higher because it's just more. The other thing is the hotter the object, you're going to see that actually it's going to emit more in these shorter wavelengths because these are more energetic. So its curve will be higher and it'll be kind of skewed over here to short wavelengths. Those two things. And then this actually is something we'll kind of bring up here in a little bit. But if an object is a good, absorbs energy good, it also emits energy good. So something that, and what it's going to come down to, honestly, so if I tap my feet, I'm tapping on the geosphere. Okay, as it turns out, the geosphere, it fits this bill. It's a great, the Earth is a great absorber of energy, and it's a great re-emitter of energy. Okay, so those are 4 laws of radiation. So I kind of told you that I'd show you kind of how the sun's, I guess to me I'd call this kind of a profile. This red curve here is kind of the energies that the sun is sending out. Okay, notice that along the x-axis, we do a lot with graphs in here, don't we, charts and stuff. Along the x-axis we have wavelength, we have short over here, and we have long over here. Okay, so the sun kind of has this sort of emission going on. Now we're going to talk about, the sun is oozing all those energies, but they interact with the Earth's, they don't all get through the Earth's atmosphere, I'll just put it that way. One of the things, and I know this isn't astronomy, but honestly, we can get a kind of a profile of other stars, and we can, just by the energy they're sending, know what the surface temperature of that star is. So the surface temperature, this profile corresponds to 10,000 degrees Fahrenheit is the surface of our sun, which is about right. It's about 6,000 Kelvin, okay, 6,000, yeah. But anyway, all right, so that is the sun. What do you think the Earth's going to look like? Or, yeah, the Earth. Is it hotter or cooler than the sun?
It's cooler.
It's cooler.
But much shorter.
Yep. So, exactly. So, here's the Earth's cute little profile. Is that not adorable? So, it's squatty, according to one of the laws of radiation, okay? and it's skewed over here to longer wavelengths. It's so adorable. And I brought this. Anybody know what this is? The temperature thingy. I love it. They are so fun. Oh my gosh, you could do this all day, you know? 84. And so the way this works, and that says 74, the way this works is it is actually, when I point it over there, now some of you guys who know what this is.
I've never seen one of those.
Really?
Never.
Oh
I
yeah.
think she was gonna shoot herself.
Oh yeah,
No,
sorry.
no.
Yeah, it's not seriously. But like fire people use these because they can indirectly see what's a hot spot and what's not.
Their shows like the color of it. Like they
Oh,
have a
cool.
screen and you put your hand
Yeah, you
like
could
this,
have
and it will show your handprint.
That is so cool, and it's just a thermal radiation thing. It's responding to that energy.
Our school.
But what this does is the red dot is not anything other than telling you where this is directed. So right now this says 74, okay? So I didn't have to take my thermometer and go over there and paste it up. This actually is looking at the IR radiation coming from that. So I could go over here. This is actually great. I'll put it by that. Yeah, see that says 70, 71 by the window back there. So I use this actually in my house to see where I need to fix my windows. You know, my cool spots, yep. It's a, yep, money saver. Okay, but that's what it's looking at, infrared radiation.
How much are those?
This one, my son-in-law told me to get it. It was like 30 maybe. It's not bad.
The school, centrally has one, and it's huge.
Mm-hmm.
And we have to go water sampling even when it's freezing out, or we did anyway.
They say they have to go water sampling when it's freezing out.
And
All
so
right.
you'd have to point it at the water, and it's got a surface and then a water one where you
Okay.
can take the thing out.
That's neat to get water temperatures.
Yeah, we were told not to break it because it's like a lot of
Well, you know,
money.
they may have a fancier. She said that theirs was very expensive, but mine, I'm thinking 30 from Amazon. You can get anything on Amazon. Oh my gosh. Okay, so that just a minute ago we saw the radiation curve from the sun. So the sun is sending us all sorts of energies, but as some of you guys know, we get like biological mutations if we get some of these, you know, exposure to gamma rays or X-rays, you know, that could be an issue. So as it turns out, these wavelengths actually are blocked by the Earth's atmosphere. That's kind of nice. So what gets through the Earth's, remember the Earth's atmosphere is really kind of thin compared to the geosphere. So the atmosphere, so what gets through the atmosphere? Well, it depends upon which energy it is, and it depends upon what's in the atmosphere. Okay. Okay, so there are three options. Three things that can happen with regard to a particular energy and something that's in the atmosphere. And they kind of make sense. The first one is basically the particle blows off the particle doesn't care that the energy is there, and the energy doesn't care that the particle's there. That's transmission. Basically goes right through. Okay. The next two is there's some sort of interaction. That particular, depending upon the energy, depending upon the particle in the atmosphere, that energy actually could be absorbed or in part by the cute little particle. And we're going to see here in a minute, the next slide, absorption tends to go ahead and increase the kinetic energy of that particle, and it's warmer. Okay, heats up the particle. The last one is, again, depending upon the energy and the particle, it could be just redirected. And there's a couple different things. It could be like a mirror. Basically, the incoming energy hits the particle and it just kind of goes back, reflected, or it could be kind of what we call scattered, which is just more of a random, takes the energy and it sends it on a different direction. Okay, so now here is the problem I have with this figure. If you're like me, I'm like, dude, they just picked, this looks kind of partly cloudy, okay? So they're trying to, it's an energy balance, or they're just trying to say what happens to the energy coming from the sun. Well, it depends on how thick this cloud is. Okay, it depends on how much cloud cover we have, and the cloud cover is not all created equal, because some of the thick clouds that we see, actually they do a better job at absorbing and scattering light than the other. But in general, if we go ahead and take 100 units coming from the sun, maybe in this partly scattered situation, we have 50 units that make it past the clouds, and the other 50 are either absorbed or kind of absorbed by the clouds or kind of scattered back. So we've actually got another figure coming up. Oops, not quite done. Meteorology? Yeah. That's okay, don't worry about it.
I've done that.
But we have another figure coming up in this unit that's gonna do even more of a closer look at this energy balance thing. Okay. So actually, that makes a good place to stop. We'll pick up here, and I don't know if we'll get through this all. We might on Wednesday. If we do, then your Chapter 2 assignment will be due Friday. If we don't, then your Chapter 2 will be due Monday.
Okay, and then
So when's the test?
I don't know, I'd have to look on your thing. It's the week of the 11th.
I don't know if it said that, but
Yeah,
I don't
I'm